taking this Lewis dot structure and showing what it looks like in terms of its geometry, we start spacing out in terms of molecular geometry. Giving a rough sketch, we end up with a true shape of our molecule in terms of this configuration. So last chapter we practiced just drawing Lewis dot structures. What we're now trying to do is take a next step and say, okay, now what does it really look like in terms of a three-dimensional geometric shape? Spacing out the electron domains as far apart from each other. That's what the VSEPR theory does. Valence shell electron pair repulsion theory. That's VSEPR. Create bond angles to separate out with the maximum amount of space between them. And this would be about 120 degrees for a bond angle. Electron group geometry. Oh, by the way, that's the direction we're heading, taking each one of these geometric shapes and just kind of going through examples of each. This is a chart from our text, coming up in the notes one at a time. So, just to show electron group geometry one at a time, we have 5 basic arrangements of electron groups around the central atom. 5 different ways they can arrange themselves. They can be linear with 2 electron domains. They can be trigonal planar with 3 electron domains. Let me go ahead and make this just a little close up here. There we go. 2 electron domains shown a linear geometry. 3 electron domains, I can see a trigonal planar geometry. With 4 electron domains, we start to see a tetrahedral geometry. The fifth has 5, 1, 2, 3. The fourth shape has 5 electron domains. It's called a trigonal bipyramidal. Trigonal bipyramidal shape. And the fifth has 6 electron domains. Octahedral will be the name of the 6 domains. This text, this chapter is just going to share with us one at a time each one of these and explain some examples of how we can create these shapes. But just to kind of put it all in one spot first, we have 5 different electron domain geometries based on bonding and non-bonding pairs. Within that number of electron domains, we start to visualize the 3-dimensional structures of our molecules. So if we have linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral as the 5 choices. Now that's really the whole chapter all on one sheet. The first of those 5 basic arrangements is what's being discussed here. So electron domains have 5 basic arrangements based on the maximum of 6 bonding electrons. Though there may be more than 6 on very large atoms, it is very, very rare. The most common is tetrahedral. You have to expand the octet to get 5 electrons or 6 electron domains. Each one of these 5 basic arrangements results in 5 different basic electron geometries. In order for the molecular shape and bond angles to be a perfect geometric figure, all of the electron groups must be bonds, and all the bonds must be equivalent. Let me blow that back out here so we can see all on one slide. Again, we're on slide 9, just kind of reading through. So keeping in mind 5 basic shapes. For molecules that exhibit resonance, and that's more than one correct structure, drawing for our double bond to single bonds, it doesn't matter what resonance form you use. The electron geometry will be the same. Just to remind ourselves, resonance occurs if we have alternating double single bonds. We drew, as an example in the last chapter, the benzene molecule, C6H6, where we said the corners of this benzene ring were carbons, and alternating between the carbons were double single bonds. A resonance structure simply shows that I could change the location of those double bonds and really end up with the same structure. The resonance structure is really just the location between 2 equivalent equal points for double to single bonds. So thinking about electron domain, it really won't change the way that we arrange our atoms. The first of our 5 electron geometry domains is going to be called linear. Back to this sheet here, the linear electron domain with 2 electron domains from the central atom. When there are two electron groups around the central atom, they will occupy positions on opposite sides of the central atom. Again, if I have a center, I want to place the electron domains as far apart from each other as possible, which of course would be a straight line of 180 degrees. This results in the electron groups taking a linear geometry, where the bond angle is 180. One example would be beryllium dichloride. Beryllium chloride here, central atom of beryllium, and two electron domains, each of those being chlorine. Here's a second example of a linear geometry. Notice here carbon is the central atom, and even though these are double bonds, they still count as one electron domain. There are two electron domains. Both are bonded. So looking at our chart, you can clearly see the only way to create a linear molecule, two domains, all are bonded, so there's zero non-bonding. It's got to be linear. Coming off of a central atom, going in opposite directions, we see a linear molecule. Carbon dioxide is linear. The linear geometry clearly shows a 180 degrees. This is just a picture showing two balloons tied end to end create a linear electron cloud, linear geometry. The second of our five is called trigonal planar electron geometry. Just to go back to this chart, and I'm going to keep showing this to kind of clarify the whole chapter in one spot. If there's three electron domains, the electron geometry would be trigonal planar. We can see two different molecular geometries based on how many bonding and non-bonding pair we have. So within the electron domain geometry of trigonal planar, there's two different molecular geometries. If we have all three bonded back to the central atom, we'll have it called trigonal planar. If only two of the three are bonded back, it will be a bent molecule. Trigonal planar and bent are the two possible molecular geometries for three electron domains having a trigonal planar electron geometry. Back to the PowerPoint, that's what this slide is showing. When there are three electron groups around the central atom, they will occupy positions in the shape of a triangle. The shape of a triangle creates the largest bond angle to separate those, as in boron trifluoride. Chapter 9 showed us the electron dot structure with boron as the central angle, fluorines coming off in each direction. The jump from chapter 9, from just connecting back to the central atom to actually showing the geometry, creates bond angles according to the Vesper theory. We want to separate those angles as far from we can to alleviate crowding within the molecule. Valence shell, electron pair repulsion. I want to separate them out. And if there's three, we can see the shape of a triangle with 120 degrees as a bond angle being the largest possible domain. And that's what this picture is showing here, a close-up of the trigonal planar geometry. Central atom, this would be boron trifluoride.